Hello everyone! In this video, I will be discussing Newton's second law in terms of constant velocity and motion, and I will be comparing a computational model to a real-life model of a ping pong ball rolling across a table. The purpose of this lab is to apply the laws of physics in a computational model to observe how velocity changes as a constant rate while using a constant force. Newton's second law relates the interaction between system and surroundings to the observed motion, or changes in momentum, of the system. In this experiment, the system is the ball and the surroundings are the rest of the environment around it. Newton's second law also states that the force acting on an object is the product of its mass and acceleration. The results of the lab illustrate how the experimental model and the predicted model are different. This is most likely due to experimental errors in rounding, mass, etc. This slide illustrates the experiment of rolling a ping pong ball straight across the table. The software tracker was used to record the object's position and time as the ball rolled. The values obtained from tracker allowed for the initial position and the initial velocity to be found, as illustrated here. The initial position was found by looking at the x and y values in the table and tracker at time equals 0 seconds, and the initial velocity was found by taking the first two positions, subtracting them, and dividing that vector by the delta t between times 1 and 2. The values for initial position and velocity were then put into GlowScript to create the computational model of the object's predicted motion. In terms of editing GlowScript, parts of the starter code were changed in order to better fit Newton's second law. The ball's velocity equation was compared with the equation to the left, and the position equation was also compared to the equation on the right. The ball's mass was changed to SI units of kilograms, and the initial conditions were also updated. The F net was also updated to be 0, 0, 0 because the ball is in constant velocity, so there is no acceleration, and thus no net force acting on the ball. For the graphical results, it is clear that the model line is more linear and the experimental position has a steeper slope and is not as linear. The graphs can be compared by the fact that both are negative sloping and in a similar trend. The discrepancies between the two lines could be due to experimental error, like inaccurately tracking the ball on tracker, rounding calculations, or the fact that the ball naturally will slow down as it is being rolled. Additionally, there's a fundamental error in this lab, which is the negligence of including air resistance. The presence of air resistance helps support the differences between the predicted and experimental data. If the y-axes were interchanged, the object would be moving in the opposite direction. If the x-axes were interchanged, the graph would move from quadrant 2 to 3 instead of moving from 1 to 4. All of the data would be inverted and thus nullified. However, the relationships between the experimental and predicted graph would not change. Additionally, it is not possible to say how many pushes and pulls are added together to get a zero net force. We are assuming that there aren't any forces acting upon the ball, thus the velocity isn't changing, which in turn makes the ball move in constant motion. To have a net force of 0, frictional forces and the applied forces must cancel each other out. In this experiment, the applied force was negated by the frictional force, which stopped the ball from accelerating. Overall, this experiment was key in examining Newton's second law while comparing the observed motion to the modeled motion. This experiment helped explain how aspects of Newton's second law came into effect. Thank you for watching.